Hi, my name is Chris Summers, and welcome to my presentation on aircraft mishap trends for Management 530. All data used for this presentation was from the FAA's database, and the terms mishap and incident are used interchangeably. When looking at the data set, I look for trends that would help prevent future mishaps. While the data might not necessarily reveal causation, it might show correlation. It is important to note that the FAA investigates every mishap to identify a cause. I will discuss that a little bit later on. Based on this dataset, it would have been virtually impossible to identify a root cause myself, therefore I looked for correlations. All of the charts and graphs within this presentation attempt to identify trends and correlation based on assumptions about population demographics and landmass size. I looked for correlations in those demographics between the number of incidents in a region and by state, pilot experience level and age, proportion of specific manufacturer ownership, and even work schedules. This first chart shows the total number of aircraft mishaps by a FAA air traffic control region by percentage. Most of the regions are fairly balanced, with the West Pacific region being the heaviest by 3% over South and Southwest. In theory, heavier population density should see more mishaps. The population density theory is even more apparent when shown by state. Here on this next slide, I have it organized alphabetically by state. California, which had a population of roughly 54 million in the 2018 census, accounted for 12% of all the mishaps. Florida and Texas accounted for 10% and 9% respectively. These states all have sizable populations and are also sizable land masses. The number of incidents in each state may correlate to its population, landmass size, or both. The correlation may even extend to demographics regarding income levels, proportion of retirees, and even weather patterns. This next chart shows mishaps broken down by time of day. I organized the data and classified it by average daylight hours during that time of year for the data set, which is January through June of 2015. Pilots log day and night time by sunrise and sunset. Night hours can only be counted as such if it is an hour past sunset. You can see by looking at the chart that the majority of mishaps occur in the afternoon. My theory is that it correlates to work schedules. Private pilots are most likely to go to work in the morning, which was the other largest occurrence of mishaps looking at the chart, and they either start their workday early or they leave early to go fly. Therefore, the majority of the flights and the mishaps should occur in the afternoon because of the higher potential. This next chart shows the number of incidents by pilot age. There are two interesting trends here. From roughly 25 to 36 years old, there's a small rise and fall, which most likely reflects inexperience. The second is a major spike in mishaps between ages 49 to 77. There are two possible reasons for this. Either inexperience or, potentially, overconfidence. Pilots in this age group are either brand new or they've been flying for a long time. It's also likely that by proportion of certified pilots, this age group is more dense. Many of these pilots in this latter age group, have higher disposable incomes, having worked roughly 25 to 30 years of their professional lives, and they're generally college educated. So in the oldest ages of this chart, it's also likely that there are a limited number who are still able to obtain an FAA flight physical to retain their private pilot's license. Speaking of inexperience, this scatterplot shows mishaps by pilot hours over the past 90 days against their overall total hours in the incident model. For the sake of easier representation, total hours were limited to 3,000 or less. There were not many pilots in the data set with more than that, and leaving them in the chart made it extremely difficult to see any trends. Note how the vast majority of the incidents occurred near the less than 50 hours over the 90-day mark. Flying is a perishable skill, and the less recently proficient a pilot is, the more likely a mishap is to occur. There is also a spike between 750 to 1,000 hours. This is a known period of overconfidence for pilots, which also leads to mishaps. Finally, when we look at the number of mishaps by aircraft manufacturer, we can see which ones are the most popular. Cessna, by far, had the most incidents, followed by Piper and Beechcraft. All three of these companies are hugely popular manufacturers of private and executive airplanes. It is a relatively safe assumption to say that the number of mishaps by manufacturer is reflective of private ownership rates. Further analysis by specific model from these manufacturers might help determine potential commonalities when looking for defects of airworthiness. From this data set, there are a number of observational conclusions that I drew. Pilot inexperience and/or unfamiliarity with an aircraft seem to be the leading causes for mishaps. Unfortunately, time is really the only counter for that problem. However, that's the reason why there are specific training requirements and adherence to checklists and all standards is expected of pilots in order to mitigate human error. I will also add that as an aviator myself, there are appropriate times when you may need to deviate from established standards or checklists, but those occurrences are rare and few and far in between. When deviations start to become the norm, that is when problems happen, and that's when mishaps occur. Looking toward the future for data collection and data quality, the FAA should consider a few things here. The first of those is simplifying and standardizing the way they input data into the database. The original data set had multiple duplicate columns that contain the same data, as well as an extensive number of columns that, when input into Excel, were completely blank. That kind of begs the question whether or not, if they're collecting information on these categories in other data sets, or if there is an actual need for these categories to exist. Standardization was also a problem that I encountered with this data set. I would have liked to produce some visualizations, such as a comparison of mishaps by manufacturer and engine metals for Cessna, Beechcraft, and Piper, but after nearly an hour of trying to standardize the entries for just Cessna, I gave up because they were so varied. There's another small piece I'll show you here in a second on standardization, but since we're on the topic of visualization strategies briefly, I just want to mention that I would have liked to produce some graphics on phase of flight and possibly weather patterns other than runway conditions, but there weren't any instances of that data being included in the set. And definitely on the subject of standardization, a lot of the entries in the data set did not contain any information on runway condition because the mishap did not occur on the ground or during a phase of flight that would be takeoff or landing. So therefore, the information was excluded from the data set. But now moving on to the piece about primary factor codes that I discussed in the introduction. Standardization, you can see on the Excel image that I have here with the highlighted columns. What we really have here is repeat information. The highlighted column on the left shows the initial primary factor cause code, but then those same first two numbers are included in the second highlighted column on the right. The problem with this is there's no easy way to classify them because the subcategory is the second two numbers in that right-hand column. So I have no way to graphically depict primary factor cause code and a subcategory of that at the same time. It's also worth mentioning that these factor cause codes were discontinued in 2015, so this data set that I use would have been the last year that these codes were included. So any feature analysis might have some kind of a different system if I were to look at a different data set. On the subject of data validity, I want to bring up human error here. So this particular chart that's included with the Excel file here, Excel image, shows one of the problems with human error in the database that was used to produce these graphics. So if you notice the data validity column and everything underneath it says valid, I actually had to write an if-then statement to compare values of pilot hours over the last 90 days versus their overall total hours. Because of human error, some instances pilots were logged with more hours in 90 days than they had total hours as a pilot. So naturally that's problematic, making those particular parts of the sample set invalid, and they were therefore excluded and they were deleted from the data set for analysis. Standardization can help overcome some of that human error, but still, even though there are different functions, such as the function Excel that allow you to do a data validity, if you don't ask the program the right question, it won't give you the right result. So to really summarize the overall presentation here, we do have a number of trends that exist within the data set. They relate to the pilot's age, how proficient they are, how much they've flown in the last 90 days, or overall as a pilot, how much they've flown in that particular model versus other models, the time of day that they're actually flying. Are they flying in the afternoon? Or are they flying in the morning, which the majority, the first and second categories of those incidents happened. And then looking at manufacturer ownership proportions as well. Remember that Cessna, Beechcraft, and Piper all had the largest preponderance of incidents, which is probably because they're all so popular. And then we also looked at by state and by region, which for further analysis we could look at population demographics and through those state and regions to determine if there are any other correlations that exist there. Really, as a whole, this data set wasn't particularly useful for identifying trends in causation. We did see correlation, but because of that issue with the primary factor codes, we didn't have enough data to actually analyze either by primary category or subcategory, and it used a system that's completely obsolete, so it was really irrelevant for this data set. And then finally, as a last point, human error is really only mitigated by standardization, so your data set is only as good as the validity of your data. If you don't ask the analysis program the right questions, you're not going to get the answers that you seek, and there you won't be able to produce the results that you want to, or any actionable results that will help you improve training programs in this case, or if you have a separate business problem, it can be applied to that. Thanks for listening, and I hope you guys enjoyed.